Hello everybody, Nerdyology here, and back to you with another chem video, and this one is the 2020 US National Chemistry Olympiad Local Section Exam, problems 13 to 24. So let's begin. So the first problem tells us, which gas has an diffusion rate closest to half of that of oxygen gas at a given temperature? Now, you have to remember this equation. So rate of effusion for molecule 1 is the same as the rate effusion for molecule 2 is equal to the molar mass of molecule 2 and the molar mass of molecule 1. Now we'll give oxygen a relative rate of 1. So just put 1 here, and then our molecule of interest has half the relative rate. So then our molar mass of oxygen is 32 and the molar mass of our molecular atom of interest is X, or M2. And solving for molar mass of 2, it will give us around 128 grams per mole, or that's xenon, and that is D. So moving on to 14. Which compound has the highest normal boiling point? So I think these compounds are all isomers. Compounds are all the same molecular formula. So how would you distinguish between the intermolecular forces? Well, they all has the same LDF or similar, right? And they all have hydrogen bonding. But no, that's not the case. This question is talking about assessing surface area and molecules. Now, the higher the surface area, right, the stronger London dispersion forces. The reason is that a higher surface area means that the molecules have more area to polarize their electron clouds, thus contributing to stronger London dispersion forces. Now let's draw the structural formulas. So A is, B is, C is, and D is. So it appears that A is the most least branched. It's the most longest, so it has a higher surface area, and that means it'll have a stronger London dispersion forces due to having more available area for electrons to be polarized. So A is our answer. Moving on to 15. 15 is a phase diagram question. Not too hard. So let's draw it out. I'll draw it out for you. So rhombic, mono, liquid, and gas. So let's take a look at the answers. Rhombic sulfur cannot be sublimed without first converting it into monoclinic sulfur. Okay, this one is wrong. Sublimation is where a solid goes to a gas, right? But you can easily convert a solid into a gas over here without going towards this middle portion of monoclinic. So that means A is wrong. The conversion of rhombic to monoclinic sulfur, this is wrong. So on the y-axis, pressure is there, and on the x-axis, it's temperature. Now, if you want to convert from rhombic to monoclinic, right, you have to supply temperature or heat. You have to supply heat. You have to supply heat, right? My bad. You have to supply heat. So that means it is not exothermic. You have to raise the temperature, and that'll excite the molecules more, and it'll convert into monoclinic sulfur. So it is wrong. Endothermic. C. Rhombic sulfur is denser than monoclinic sulfur. if there's a positive slope between the solid form and liquid form, it is the solids will be denser than the liquids, and it's true here. Oops, my bad. Since there's a positive slope between rhombic and monoclinic, right? That means rhombic will become more denser. Let's take a look, for example, water. Ignore what I just did before. If there's a positive slope between the two phases, that means the phase on the left was more denser. Let's take a look at an example of water, right? So we'll draw our phase structure. Right? You see there's a negative slope. There's a negative slope, right? That means the one on the left, solid, is less denser than the one on the right, liquid. That means ice is less denser than water. You know this because ice floats on water. So that means C is good. Let's take a look at D. Atmospheric pressure, monoclinic sulfur cannot be in equilibrium with liquid. Okay, this is atmospheric pressure. And over here is an area where they can be in equilibrium. So you can easily cross it out. So remember, positive slope between two phases, one on the left is denser than the one on the right. Moving on. (16) So, I want to judge in which of the ironing compounds are listed in order of increasing magnetic lattice energy. Now, lattice energy is defined by two factors. The most important being is size of charge, right? Charge magnitude. The second is being distance. So the higher the charge is, the higher the lattice energy. Now, here's an interesting question. Why does charge play a larger role than distance, right? So to answer this question, leave down in the comments of what you think, and I'll tell you if you got it right or not. It's a good thinking point. So let's begin. So in A, calcium oxide has a less magnetic lattice energy. Wrong. Calcium oxide has a larger magnetic charges, right, than rubidium iodide, so we can easily cross it out. Let's take a look at B. So, okay, rubidium iodide is less, that sounds good. Why is calcium oxide the third highest? That's wrong. All other ones have a magnitude of 1 plus charge. So this one is, B is wrong. Same thing, calcium oxide is not the highest, doesn't have the highest magnitude of the lattice energy. So we cross out C. The D works because calcium oxide is in the first in line, and then everything else works by distance. Lithium fluoride is smaller than lithium iodide or rubidium iodide, and it will have a higher magnetic lattice energy due to the Coulomb's attractive law. And lithium iodide is smaller than rubidium iodide, which has a higher lattice energy. So thus it's D. (17) Sodium halides crystallize in the rock salt structure, which has a cubic unit cell of 4 formula units per unit cell. A sodium halide has a density of 2.83 grams centimeter and a unit cell edge length of 4.62 picometers. What is the compound? So when they give you a problem like this, you need to find out the molar mass. Now how would you find the molar mass? You need two components. You need to find grams and moles. Now how would you find those two? So the moles will be a little easier to find out. So the moles, you have 4 units, right? Detailing the question. Now you're going to find the moles of 4 units. So you do the conversion unit of 1 mole. And that will give you 6.64 times 10 to the negative 24 moles. Now you find the moles. Now you find the grams. Now you use this to density. And density will equal D equals mass over volume. Now you have the density, now you have the volume. Now you can use this to find the mass. So your density is 2.83 times 10 to 2.83 grams per centimeters over centimeters cubed. Now using this we'll find M. Now volume. Volume they say to give you in 4.62 picometers. But the thing to realize is that 1 picometer equals 10 to the negative 10 centimeters. So using that you can find the volume, which is just 4.62 times 10 to the negative 10 cubed, because you have the edge length, now you're making it into a cube. And when you solve for the mass, when all units get cancelled, you get 2.79 times 10 to the negative 22. Now you found your grams and you found your moles, and you divide both of these, 2.79 times 10 to the negative 22 grams over 6.4 times 10 to the negative 24 moles, you will get the molar mass of 42 grams per mole, sodium fluoride, and that's A. This is a fun problem. So moving on, we'll go to an easier unit cell problem. The tetragonal unit cell of white tin is shown below. Each circle represents a thin atom with the gray circle sitting on the 4 vertical face of the unit cell. How many tin atoms are contained in this unit cell? This is a common problem on the USNCO, especially the local exam. So this is a free point where you just notice one piece of information. So when you see a unit cell, the corner atoms equals 1/8 of an atom when you're counting it. The face is 1/2 of an atom, and the body is 1 atom, right? So yeah, using this information, you're just going to count. You're just going to count and find the number of atoms. So let's begin. So there's 8 corner atoms, right? So when there are 8 cornered atoms, they count 1/8 to an atom. And then there's 4 gray atoms on the faces, so 4 times 1/2. And then you have 1 atom, it's kind of hard to see, but you have 1 white atom in the center, so that's 1. This gives you 4 atoms, or B. Pretty easy stuff. Moving on, 19. So, what is delta HF formation? So, the thing with delta HF formation, it's enthalpy when you form 1 mole of a compound or product from its pure elements in standard state. So, with 2 of those in mind, you can do some crossing over. So, A looks good. You're forming 1 mole of product from the elements in its pure state. So, A is good. B, you're forming 8 moles of product? No, it must be 1 mole. Same thing goes for C. So you can cross them out. Let's go with D. No, the reactants are not elements in their pure form, so you cross out D. And the answer is A. Alrighty, moving on to 20. 20 is just a standard calorimetry problem your teacher gives you on your AP Chem homework. So it's nothing too hard. So let's define our system and surroundings. So our system will be the ice. So let's read the question. A 2-gram sample of ice at 0 Celsius is placed in a 50 grams of water initially at 25 in an isolated insulated container. What is the final temperature after the system has reached equilibrium? So as I said before, the system will be our ice and the surroundings will be our water. Now you notice Q sys equals negative Q sir. So let's begin writing our algebraic expression. So you have ice at 0 Celsius. Now if any heat is applied to it, it will melt. So we need to find out how much heat is required for ice to melt. So we have delta H of fusion is 0.61 kilojoules per mole. So then we'll convert our 2 gram sample of ice into moles. So by doing this, 2 grams over the molar mass of water. And then we'll do, we'll multiply by the heat of fusion in joules per mole to account for the unit. So that's 0.610 joules per mole. Then you need to account for the temperature increase in water by doing 2 grams of water times the specific heat capacity times X. X is final minus 0, which is initial temperature. Then we do minus the heat gained by the surroundings. Or, in this case, heat lost by the surroundings. So that means we'll and you can calculate it by measuring the temperature change of water. So 50 grams of water times the heat capacity times X, the final temperature of water, minus the initial temperature of water. And then when you solve for X, the final temperature of the system, when it reaches thermal equilibrium, X equals 21.0 Celsius, or A. Moving on. 21. This is just a nice and easy plug and chug. So you must remember one thing, that a substance boils when its vapor pressure equals atmospheric pressure. So the normal boiling point is the temperature where a substance boils at an atmospheric pressure of 1 atm. So using this knowledge or information, you can find the vapor pressure at a different temperature. We shall use the good old equation Clausius-Clapeyron. So this equation is natural log of P over 1 equals delta H over R, temperature of 1, temperature of T2. Now if you're struggling to remember this equation, just look on your equation sheet and search up the Arrhenius equation and replace the activation energy with delta H and the rate constant with partial pressure, and you'll get this equation. So then we just plug and chug. So we're going to solve for the pressure. This is the vapor pressure. So this is the vapor pressure, right? And the vapor pressure at the normal boiling point is 1. So we'll keep in mind of that, and you just plug in the values. This has to be in joules, not kilojoules. And then 3.153 minus 3.18. That, and using some algebra and logarithm rules, you'll get pressure to equal 0.25 atm, or A. Alright, not bad, not bad. Okay, 22. Now this was a pretty challenging question in my opinion. It's something different than your regular thermal questions. So it's one of those questions where you spend a little longer in the exam. But you have plenty of time, so don't worry guys, don't worry. So let's begin. If the average carbon-hydrogen bond dissociation enthalpy in ethane is 416 kilojoules per mole, what is the bond dissociation enthalpy of the carbon-carbon bond ethane? So the key thing to realize is that the sum of the bond energies equals the dissociation enthalpy. So now here's what I mean. So dissociation enthalpy is this, C2H6 over 2C plus 6H, right? Now you can find delta H of this reaction by using the heats of formation given in table by this equation. Now when you use this equation, right? So when you use this equation, alright, this will give you just find the sum of the delta H of formation, the products times the stoichiometric coefficient minus the sum of the delta H of formation, the reactants, times its own stoichiometric coefficient. And this will give you 2.829 kilojoules per mole. Now, the sum of the bond energies or enthalpy will equal this, because to break each of those bonds, to break this atom into its own individual, to break this compound in its own individual elements. So with this realization, you can use some algebra. This reaction enthalpy equals, so now you need to draw the Lewis structure of ethane, and it's an alkane, right? So you draw, this is the Lewis structure. Oops, right? So you draw the structure. There is 6 carbon-hydrogen bonds. So that means we do 6.146, and there's 1 carbon-carbon bond plus X. Now, X in this case equals to be 333 kilojoules per mole, and that is B. So this is a new problem, and it's a different problem. The local exam, even the local exam has different problems every year that may look tricky, but remember to keep your cool and solve them. Alright, last 2 questions of today. 23. This one is not that bad. So a reaction has an equilibrium of 20 at 298, and K equilibrium increases with increasing temperature. Now, since K goes up with increasing temperature, delta H must be greater than 0. And also, since K is greater than 1, delta G must be less than 1 too. Okay, now we satisfied option 1. But then, will option 2 be satisfied? And the straight and simple answer is yes, it will be satisfied. Delta S is greater than 0. But you know why? Let's take a look at the equation. Delta G equals delta H minus T times delta S. For if delta G was negative and delta H was positive, delta S must be positive too to make delta G negative, right? If this expression was positive, this will become big enough and offset the positive delta H by subtraction. It will mathematically work out. So that means option 2 is good, and that means it's C. C. (24). Alright. This one is a question I like, because it combines, I think, multiple topics. So a sample of water in a movable piston maintained at 100 Celsius with an external pressure P. Which statement best describes the transformation of solid liquid into water vapor? So I think this question implies that external pressure is 1 atm, because at that temperature of 100 Celsius, it is implying that it's the boiling point of water. So the external pressure in this question is 1 atm. Now we can cross out A and B. The reason why we can do that is, think about it. So we have our own container, with a movable piston. If the external pressure is greater than 1, that means the pressure inside, the volume will be smaller and the pressure will be greater than 1, right? And since water has a fixed vapor pressure at a fixed temperature, right? Its vapor pressure won't equal the pressure inside the container, in the sense that the pressure inside the container is greater than the vapor pressure of water. So water doesn't have the force enough to boil. Like, the bubbles inside cannot move up. So A is out. And it also says, you can also cross out B. So let's talk about C and D. Now, it's a little trick question here. It's non-spontaneous when the pressure equals 1? Because that's what C is implying, right? But that's wrong. If the external pressure was 1, right, water would still boil. Because its vapor pressure equals the pressure outside. So water has enough momentum or force to like push bubbles outside in the air. So you can cross out C. And D says it is non-spontaneous if the pressure is greater than 1, which is true. Water cannot boil because the inside pressure becomes greater than 1 as well because volume goes down. So then D is the correct answer. Thank you guys and have a good day.